All right, welcome to Chapter 8 in AP Statistics. Today we're taking a look at the basics of confidence intervals. What are they? How do we construct them and how do we interpret them? So we have a lot of objectives for this lesson that we're going to go through today. We're going to determine what's called a point estimate and a margin of error from a confidence interval. We're going to interpret a confidence interval in context, interpret it in the confidence level in context as well. We're going to describe how the sample size and confidence level affect the length of the confidence interval, and we're going to explain how practical issues affect and the interpretation of a confidence interval as well. So a lot to get through here. Let's say we had this example where the teacher had a specific mean in mind, call it mu, and they stored it into a calculator as m. Now let's just say that you were given some information here. If I stored that m into your calculator and then you ran this calculator function where you found the mean of a rand norm, okay, so that's a distribution of that is normally distributed with mean m with standard deviation 20, and you collected 16 of those numbers. And when you ran that, you end up getting a mean of 240.79. Now again, keeping in mind that that is 16 observations with the mean m and standard deviation 20. If you were to be asked how to give a range of plausible values for what you thought m might be, how would you do that? Take a moment, pause the video, think about it, and maybe jot down what you think a range of plausible values for that m value would be, keeping in mind that it's probably going to be somewhere around 240.79. But I mean, do you go just 1 or 2 below that? Do you go 20 or 30 below that? And how much do you go above that to get this range of plausible values? And keep that in mind as you go through this video, because we're going to be referencing this guess as we go through. So what we just went through, what we just talked about with that mystery mean example, was how to come up with a point estimate or a value that we think might represent the population. And that's what we refer to as a point estimate. Now, your point estimate is probably going to be coming from either x bar or p hat, depending on whether we're dealing with means or proportions. But what we're doing is we're taking that x bar or that p hat and trying to learn something about the population. So a point estimator is a statistic that provides an estimate of a population parameter. So x bar is estimating mu, or p hat is estimating p. So the value of that statistic from the sample is called a point estimate. Now we talked about last chapter the idea of an unbiased estimator, and that is when we have a sampling distribution, meaning if we have all possible samples of the same size, then we know the mean of x bar equals mu, or the mean of p hat equals p. But when we're just talking about a single individual sample, we can't assume that x bar equals mu or p hat equals p, because there's a lot of variability from sample to sample. So when we talk about this idea of that range of plausible values for what the true mean or the true proportion could be, what we're really talking about is creating a confidence interval. And that's what this chapter is all about. It's creating confidence intervals and interpreting them. So when we talk about what's a confidence interval for this mystery mean problem where we had this value of 240.79, well, we would probably say it's going to be a little bit less than that and a little bit more than that. All right. How would the sample mean x bar vary if we took many SRSs of size 16 from the population? Well, we know that it's going to have the standard deviation of 20, but we also have to keep in mind that the sample size is 16. So what that really means is that the standard deviation of the sample is really 20 over the square root of 16, which is really just 5. Now, we could take multiple samples and see that we could get different values for that x bar there. And what we would be looking for is to see, well, how far should we go on either side to ascertain an interval of range of values there. So it says to estimate the mystery mean mu, we can use x bar equals 240.79 as a point estimate. We don't think mu is exactly equal to that, so we have to say how accurate we think our estimate is. Well, if we were to take repeated samples, the values of x bar follow a normal distribution with a mean and a standard deviation 5. All right. Now, if we were to try to think of it from the 68, 95, 99.7 rule, we would be looking at 68% of observations are going to be within 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. So if we wanted to say be 95% confident, which is a fairly common confidence level, then we would go out 2 standard deviations in either direction. Well, we just said the standard deviation was 5. So if we double that to go out 2 standard deviations, then we'd be going out 10 in either direction. So what that means is, even though we don't know what mu is, if we subtracted 10 and we added 10 to that, then we would say that we are 95% confident that the true mean is going to be somewhere in between that range of values there. Now we don't know mu, so we're going to be using our x bar to estimate that. So what that means is we would estimate that the mu, the true mean value for m, is somewhere between 230.79 and 250.79. Again, just taking that value of 240.79 and subtracting 10 and adding 10. And if we did that, we'd be calculating an interval using a method that captures the true mu, the true mean, in about 95% of all possible samples of this size. So the big idea of what we're doing when we construct these confidence intervals is we're starting with some point estimate, and again, that estimate is either x bar or p hat, and then we're adding and subtracting the margin of error, so how much we think we need to go out in either direction to be pretty confident that we're containing the true mean or the true proportion. Now, what you need to think about is the relationship between the margin of error and the confidence level. We refer to the confidence level as uppercase C, and it says the confidence level C gives the overall success rate of the method for calculating the confidence interval. In other words, in C% of all possible samples, the method will yield an interval that captures the true parameter value. So if we were to be using this 240.79, that's one sample. It doesn't mean that we're 95% sure that we're containing the true mean if we subtract 10 and add 10 to that value, because we need to think of our sample as one of many constructed in the same format. And that's kind of a tricky thing for students to understand. We need to think of it as one of many samples constructed in the same manner, and 95% of those confidence intervals would contain the true mean. So that's basically the idea of confidence intervals and confidence levels. Now, we could have any confidence level we want, but we're going to kind of save that conversation for the next video. It says here the confidence level is the overall capture rate if the method is used many times, as I kind of just went through there. So if we look at this here, we could have a sample of 240.79 as we got, plus or minus 10, or if I did it again, maybe I got 246.05 plus or minus 10, 248.85 plus or minus 10. If we did this many, many times, 95% of the time would these confidence intervals contain the true mean. And if you look at this here, let's just say this green distribution here is the true population distribution. And each one of these individual bars down below, they represent different confidence intervals. And I believe there's 25 of them, 25 confidence intervals constructed. And as you see, all but one of them extend to the true mean mu, this vertical black line there. So 24 out of 25, which is 96%, actually contained the true mean. And this is using a 95% confidence interval, so that's pretty close. Now, if we were to do this instead of 25 times 250 or 2,500, we would see it even get closer to 95%. There's still going to be some variability in small sample sizes. So, interpreting confidence intervals. Here's the sentence that we want to get to know to be comfortable with interpreting. Because we're blank % confident that the interval from blank to blank, meaning your lower and your upper value, captures the actual value of the, and then you fill in whatever the population parameter that you're referencing, and keeping in mind that you make sure you put it in context. All right. If you were to try to interpret that, basically it says if we take many samples of the same size of population, about 95% of them will result in the interval that captures the actual parameter value. So the top interpretation is when you're plugging in your actual values for a confidence interval, and the bottom is just kind of like a more conceptual understanding of what a confidence interval is. So it says the confidence level tells us how likely it is that the method we are using will produce an interval that captures the population parameter if we use it many times. Confidence level does not tell us the chance that a particular confidence interval captures the population parameter because it either does or it doesn't. So it's either 0% or 100%. But we need to think of it as a range of plausible values for the parameter. And it says we interpret confidence levels and confidence intervals in much the same way, whether we're estimating a population mean or a proportion or any other parameter. As we'll see later on in the course, sometimes we want to do a confidence interval for the slope of a regression equation, but we'll talk about that later. So again, when we construct a confidence interval, we start with that point estimate plus or minus the margin of error. Okay, well, let's think about how we would do that for our mystery mean example. 240.79, that's our estimate, that's our x bar, plus or minus 2. Now, where is that 2 coming from? Well, that's coming from if I wanted to be 95% confident, that's 2 standard deviations away, according to our empirical rule with normal distribution. So we do plus or minus 2 times 5. Now, that 5 is the standard deviation of the sample. So it's not the 20 that was provided for the population. It was that 20 divided by the square root of n, or square root of 16, which is where we get that 5 from. All right. Now, this 2 value that I referenced, we could just call it the number of standard deviations, but we could also reference it as the critical value, which is how it's referred to on your formula sheet. So we should get used to that. So if I take this margin of error idea, we could break that down farther to the critical value, in other words, the number of standard deviations away from the mean, times the standard deviation of the statistic or of the sample. All right. And again, this is the form that you see it on your formula sheet. So this is definitely the one you want to make sure you get down so that you can reference it and use it when you see it on the formula sheet come the test day. All right. So we have our rule here for finding the confidence interval, but we also want to talk about some properties of confidence intervals. When we talk about the margin of error, we break it down to the critical value times the standard deviation of the statistic. The user, meaning you, who is conducting this confidence level, you get to choose the confidence level, and the margin of error therefore follows that choice. Now, for the purposes of AP, generally speaking, you'll be told construct a 90% confidence interval, construct a 99% confidence interval. But if you were doing this in actual practice, you would get to decide how confident you want to be. Now, if you think about that, you might be saying, well, why wouldn't you just always say 99% confident, because that's very confident. Well, there's a trade-off in that, because the more confident you want to be, the larger or the wider the confidence interval is. So that's something you need to be mindful of there. The third bullet down here says the critical value depends on the confidence level and the sampling distribution of the statistic. Greater confidence requires a larger critical value, therefore larger margin of error. Therefore, you're adding and subtracting a larger number. So you're talking about making a confidence interval that's wider. The standard deviation of the statistic depends on the sample size, and that's basically what we talked about in the previous chapter when we were talking about sampling distribution. As sample size goes up, standard deviation of the statistic goes down. So you can, in a way, control this part of the expression here. You can control that by increasing your sample size, and that's always a good thing to do. Not always practical necessarily, but something you want to think about. So, keeping in mind here, our method of calculation assumes that the data comes from an SRS of size n from the population of interest. If you don't have an SRS, then you have no confidence that your X bar or your P hat is going to be representing the population. So checking to see that you have collected your data in an intelligent and an ethical way is really important. It's a condition that you need to check. And the margin of error in a confidence interval covers only chance variation due to random sampling or random assignment. So that's it for this section here. And we talked about a lot of really big ideas, and obviously we'll be talking about them more in class to kind of nail the points home and make sure we have it down before we get into it a little bit more concretely. But these are the objectives that we set out to meet. Hopefully you feel a little bit better about each one of them, but we'll be practicing more in class as we move forward. That's it for today, and see you next time.